All right, so let's take a look at this. The reason that you want to try to keep it out to the hundredths place is that this is a salary, and they don't round up salaries to the nearest dollar. And if you think about it, for example, in the state system for teachers right now, if we all got our salary rounded up to the nearest dollar, that would cost millions of dollars statewide. Because, you know, even though you think, oh, it's not a big deal here to round up to the nearest dollar, but if you think about hundreds of thousands of employees. So you want to keep this out because we're dealing with a salary, at least to the cents, to the hundredths place. All right, so what's going on here? I wouldn't mind a 3% salary increase. In fact, some of you may have noticed some of your teachers are wearing little buttons because we've been without a contract since June. Anyway, I won't get into all that. So 3% is actually would be above the rate of inflation right now in terms of a salary increase. So if you can get 3% each year, at least in these days, that's going to keep your income above inflation. So notice here we have a yearly increase. And what's happening to the increase as you move up each year? Is it staying the same? No, your increase is increasing. Okay, so it's not staying the same from one year to the next. So as your years increment by one, your salary is actually going up a little more. And so the first question, are the yearly salary increases the same, constant from year to year? The answer is no. If they were the same, for example, let's suppose it was $1,200 every single year. Then as your years went up by one, your salary would go up by the same amount every year. That's your slope. That would be a slope, but the slope has to be a constant rate of change. It's either a number you add or subtract. However, these salaries are changing from year to year. The rate of increase is increasing. So this is not a straight line. And in fact, if you drew it, this is not going to be totally accurate, but I'd start somewhere over here at 40K. And that would be my initial salary. My next year, I don't get too much of a bump, right? I went from 1217 my first year. So let's say here's 1217. And then the next year I'm at 1253. Big deal, not too much of a bump. So I'm just going to do that. But each year, my salary is getting bigger and bigger, depending on my scale, right? So if you notice, these vertical drops here are getting bigger and bigger and bigger if we compare them to our initial, way down here to our initial. So if we did like a line here, you see that these vertical jumps are getting bigger and bigger. That shows the rate of change is increasing. So if you connected these salaries, you get a curve that looks like this. Okay, so this would be the number of years after 2014, and this would be your salary in dollars. So this is a different looking curve than anything we've seen prior to this. It definitely isn't a straight line because we're not adding the same amount every year to our salary, and this is the beginning of what we call, or today's topic, exponential functions. This is an exponential growth curve. That's what we call it. And if we were to write a formula for this, or a function, even though I'll take you there in a minute, this is what it would look like. Let's say we're doing S of t, S being salary over time. Our initial salary was $40,560. Is that correct? And I'm growing by 3% a year, which means I take 100% of this, and then I add 3% of it. So that's 1.03, and I put a t up here in the sky. So what's really different about this function is your variable is now an exponent, which you haven't seen any functions like this since we've started the class. This is a very different looking function. You're always used to your variable being either the base or down like a polynomial function. Your exponents were all integer values or whole numbers, all right? So this is a very different looking function. So I'm going to offer you a job right now. I'm going to offer you a job to wash my dishes. And I'm going to say the first days we're going to count as day 0, and I'm going to give you a cent. And then the next day I'm going to double it and give you 2 cents. So Sunday's day 0, you get a cent. Monday's day 1, you get 2 cents, and then 4 cents, and then 8 cents, right? 16 cents. Would you take the job, Carolyn? You wouldn't? Just for a month. Only a month I want you to work for me and wash my dishes. You won't? 30 days. 30. You'll take it? You'll take it? What about you, Alex? Would you take it? No, just a cent every day and I double it for a month. Okay. All right, well, let's take a look at this. All right. Okay, here we go. We're going to do this. I'll have to use my calculator eventually. But this is the amount in cents, all right, in cents. 1 cent, 2 cents, 4 cents, 8 cents, 16 cents. So after a week, you're up to about, 7 days, you're up to what, 64 cents? Caroline might have been the smartest person so far, saying, oh, I'm not going to get, right? So how am I growing as my days increase by 1? This is not increasing by the same amount, but it's doubling, right? So this is times 2. This is times 2. So if I take the previous salary of 2 cents to get to the next one, I'm multiplying by 2, right? So this is what we call the doubling function. So I could write this like this. F of t equals 2 to the t. Let's take a look. Because when t is 0, what's f of t? When t is 0, I get 2 to the 0, which gives me my 1 cent. When t is 1, the next day I get 2 cents. When t is 2, I get 4 cents. So let me have my calculator do this out for 30 days and see, or 31 days, and see what I get. So let's see. So turn it on, and let's turn off that equation. And let's put in my doubling. I'm doubling every day. Or it's 1 plus 1. I'm growing at 100%. Each day my salary grows at 100%, not 3% anymore, 100%. 2 to the x. And let me set my table. I'm going to start at 0, day 0, and I'm going to increment by 1. So let's take a look at how much money I'm making. As you can see, I'm up to 64 cents after the first week. That's 7 days. Let's go another week or so. 4,096 pennies. What's that? How much money is that? What's that? How much dollars? 4,090. Yeah, $40.96. Well, I don't know. It's not bad for washing dishes, right? What is it the next day? Woo! I jumped from 40 bucks to 81. I don't know, Caroline. I don't know. Now look at this. Day 14. So f of 14 is 16,384 pennies, which is $163.84. I don't know. I don't think you make that in your job, Alex. Let's go out a little further. We're not even. Oh, here we go. 19 days. Where are we? 5,24288. So 524,288 pennies. You want this job? Okay, that's $5,242.88. You still don't want it, okay. People go on Survivor to make this amount of money and kill their bodies. So here we are. Woo! Where are we? No, that's not what that says. All right, let's get that calculator back up and take a snapshot of this so you can recall that you had the offer of your lifetime. Yeah. Yeah, I know you did. You all wanted it. I wish I could pay you, but I can't. So, it's only pennies. All right. All right, so let's see how much money this actually is. Day 31, which is actually, it looks like day 30, but it's 31 days later. 1.07 e to the 9. So I want to see what that number is. Do you know what that number is? How do I figure out what that number is? Josh?
You move the decimal point over 9 spaces.
Right.
Yes, I know there aren't that many spaces, but there are zeros.
Right. So e to the 9, this is how they write scientific notation. So this is 1.07 times 10 to the 9th. So 107, let's see, how many zeros do I have to put now? 7, 1, 2, 3, 4, 5, 6, 7. I'm going to cut off 2 zeros to make it into dollars. $10,700,000. Not bad for a month's work, right? So.
Not worse than touch other people's dishes.
Oh, okay. So you're a germaphobe, huh? Okay. All right. It's gross. All right.
We only got 1,304.
All right. Well, we'll look at that in a minute. All right. So let's calm down now. I know you're all excited about hitting the big payday. So start us off here, James, with number 1. Right. So it's not growing at a constant rate like lines do, or decreasing at a constant rate. It's a constant percent rate, or a constant percentage, or a constant factor, because you're multiplying. All right, so this is a very different looking function. So now we're going to try, even though I showed it to you, let's go through how we can come up with a general formula so we really understand what's going on here. So after 1 year, we took our previous salary of $40,560. We added to that 3% of that amount. And now notice I put this as an equivalent statement. How did I go from this addition problem to this multiplication problem? Yep, Bridget?
Because instead of doing 0.3 the salary, you did 100% salary.
Right. Right. So in other words, if I had a number in front of the salary right there, it would be 1, which represents I'm taking all of that salary, 100% of it. I got 100% of my salary, and I'm adding to it 3% of my same salary. That salary is what we call the greatest common factor. You have a greatest common factor to both terms right there. There it is. There's your GCF. So when you pull your GCF out front, you're left with 100%, which represents this, and 3%, which represents this amount. So we can now take 1 plus 0.03 and call it 1.03. So it's growing because this number is bigger than 1. It's bigger than 100%. It's 103%. That's the actual growth rate. Excuse me, the growth factor. So it's growing because it's bigger than 1. You see where each of the individual parts of that come from. I take all of my salary and I add 3% of it. Okay. Now we take this, well, you called it 41,777, but I'm going to keep it in this form. This is $41,777. And you play the game all over again. You start off with 100% of that, and you add 3% of it. So when you now take this out as the common factor now is the whole enchilada right there. That's your common factor. Notice you get 100% of all of this, and then 3% of it. So you have, here's your common factor. You get 1 plus 0.03. You get another 1.03. So it keeps repeating. That growth factor keeps repeating depending on how many years you go out. So the new salary after 2 years, we can shortcut with exponents by saying my initial salary, this is my initial salary at time t equals 0. And I'm multiplying it by some growth factor here. And it's called a growth factor because I'm multiplying, raised to 2 years. All right. So if this is a pattern, how would I determine my new salary after 3 years? Can someone tell me how I could calculate that, my new salary after 3 years? Yeah. Perfect. Yep. And if you throw that in your calculator, it should be what you have along row 3. What about 5 years, Lauren? Okay. Up to the what? 5th. Okay. And 10 years, Haley? Okay. And now the general formula for any number of years, Simpson? Okay. So in general, we can say that this salary function, we can call it S of t equals your initial salary, which we know in this case was $40,560, times the growth factor. And what's the growth factor made up of? 1, which represents all of that initial salary, 100% of it, 0.03, which is the plus 3%, and then t is the number of years it's growing. Okay? So notice that this, if I used, instead of words here, I used variables, I might have it look like this. And I might use SO here to represent initial salary. Every time you use that little subscript with the little O, that means time t equals 0, initial salary. So if we're talking about money growing in a bank, we might do this, P of t, because they always use the word principal. And then I might have something that looks like this, P sub naught for initial principal. That's how much money you initially put in your investment. And then you'll see later, the rest of this formula looks like this. We'll get to that later. And I don't even know if they make this shampoo anymore, but they used to have a shampoo called Pert, and came in a green bottle. Do they still have that? And that's how I used to get students to remember that formula, like the shampoo. And if we were talking about population growth, you might use P as well. Actually, a lot of the population growth models look like this, where you have some growth factor there. So most countries have an increasing population. Right now, Germany's population is actually declining in Germany. And so this number wouldn't be bigger than 1, it'd be smaller than 1. Right? Sometimes they use Q for the number of a quantity, like this. So these are all like application of real world modeling problems. And all they do is change the variable letter to actually model the context of the problem. So in general, when we're just using regular old mathematical variables and stuff, like when we do the quadratic formula in polynomials, we do ax squared plus bx plus c. So in math, we would say, usually most of the time we're modeling exponential growth or decay. It's over time, so they often will have a time here, function of time. A is your initial amount times B. B is your growth factor raised to the t. All right, so when B is positive, this is what we call a growth, exponential growth. And when B is a fraction or a decimal, which is often how you see it as a decimal, between 0 and 1, it's a decay function. All right, so A is the initial amount. And the reason why we say A is the initial amount is because when you let t equal 0, this is what your function looks like, A times B to the 0. And B to the 0 is 1. So f of 0 is A times 1, or just A. So that's your initial amount. So that's an important point when you graph these functions. because that's going to be your y-intercept. Yep. B can't be negative. It's a fun thing to try graphing. When you try B to be negative, it goes like this. I'll show you in a minute. All right, but I want to do that with you individually. Okay. So some definitions in most books, including ours, will define your sort of basic exponential function to look like this. Notice what's the value of A in this case. What's the value of A? 1. So it's the basic function. It's like your parent function in a way. So most books define exponential functions as b to the t. B's got to be greater than 0 and B cannot equal 1. Because if you had a 1 there, it would just be a horizontal line. Y equals 1. So let's take a look at this table now and see what we can fill in here. So here's our first function. This is like doubling your penny every day. This is called the doubling function. And would this be an example of growth or decay? Growth. Okay. What about the one below that, the function p of t? Is that growth or decay? Growth, because b is bigger than 1, and the final one is decay. Okay. So the value of b in my first function, f of t, what's the value of b here? B is your base. Look up here. 2. Yep. And in the second function, p here? Okay. I'm looking for the growth factor, which is your base right here, b. See b? What's the value of b? 1.012. That's your base. That's what's being raised to the power of t. Okay. And what about for the function g? What's your base there? 0.886. Okay. So again, you know, whenever your base is a number between 0 and 1, it's got to be a decay function. Whenever it's bigger than 1, it has to be a growth function. All right, so let's take a look at now what would be the constant rate of change, the constant percentage rate of change for each one of these. Well, to get B, remember B is equal to 100 plus R. And if R is declining and negative, then it's 1 minus R. Okay, so let's take a look at this. How would I figure out what R is here? Well, B is 2, and that equals 1 plus R. So if I solve this for R, I subtract 1 from both sides, I get R equals 1. And what does that convert to as a percentage? 100%, right. So that's my rate of change when I have a doubling function. You take all of the previous amount of money and add it, all of the previous, 100% each time, not a little fraction of it like we had with our salary increase. Okay, so now the next one, we have 1.012, that equals 1 plus R. So if we subtract 1 from both sides, what do I get for the value of R here? Yeah, in the end, but what's just R itself? R's got to be a decimal. Right, so if I subtract 1 from each side, I get 0.012. Now make 0.012 into a percentage. So be careful, you go over twice. So is it 12%? 1.2, right, 1.2%. Okay. All right, now to find R in the decay function, you say B is equal to 1 plus R. B is 0.886 equals 1 plus R. And if we subtract 1 from both sides, we get R equals, and it looks like it's negative, right? Because it's declining. Negative 0.1124. Did I do that right? 114? So this would be, R would be negative 0.114, which is a decrease of 11.4%. So that's how you look at your function and you determine the growth factors. Remember, your growth factor is different than the growth rate, the growth decay rate. B is your base of your exponent, t. And when you subtract, when it's a growth, you basically subtract 1 from each of these numbers, okay? And then when it's a decay, you say, what number do I have to add to this decimal to get 1? And that will give you your decay. The number out front here is your initial amount or your initial quantity, whether that's dollars or cells growing at an exponential rate or a population. Just depends on your story and application. Okay, so let's take a look at graphs of exponential functions. And as you know, as we always start with any of these functions, we always look at our basic function. We've been calling them before parent functions. No, I'm using 2 to the x. I could look at 3 to the x, 5 to the x, 10 to the x. I'm just using 2 to the x, a doubling function. And then I'm looking at 1/2 to the x, because this has an application in a lot of science applications of half-life, which I think you may have heard of before, half-lives in chemistry. Okay, so this doubling and half-life function would be considered basic exponential functions. This being a basic growth function, this being a basic decay function. Okay, so if you were to start plotting this function right here, and you pick some values of x and put it in, so let's say -4. If x is -4, this is 2 to the -4, which is 1/16. So you can see you're really close to 0 there, right? You're really close to the x-axis. And as you increment by 1, you go up by a factor of 2. You get twice as big. 1/8 is twice as big as 1/16. -2, you get 1/4. A quarter is twice as big as an eighth. -1, you get a half. So here we are at -1, 1/2. And this point is always a very important point when you're graphing these exponential functions. Your y-intercept, 2 to the 0, is 1. Whenever you have an exponential function that has the coefficient a as 1, you'll always go through the point 0, 1. Always. Because when you put 0 in for your exponent, your base raised to 0 will always give you 1. So this is how you know when you go through 0, 1 that you don't have any kind of vertical stretch or shrink going on. Because if you had a vertical stretch, that thing would go up. And if it was shrunk, it would go closer to the x-axis. So that's one way of knowing you have no kind of shape changing going on and you have your basic function. Now, how do you find out where the base is from looking at your graph? How do I know that's 2 to the x versus 3 to the x or 5 to the x? How am I going to know that? There's one point on that graph that's always going to tell me the value of b, my base. Y-intercept right here is 0, 1. And that's always, when I put a 0 up here, I get 1. So that's not going to help me with the base. But what it does help me with, Carlton, is it tells me the number that goes in front of 2 to the x is 1. When x is 1, look what happens when x is 1. When x is 1, I get 2 to the 1, which just is my identity, too. So if you go over one step and you look at the value of your function at x is 1, that will always give you the base, as long as there's been no transformation and you're just looking at your basic function. And then at 2, you're at 4, and at 3, you're at 8, right? And it just continues like that, as we would imagine. All right, so let's take a look at various information about a typical basic exponential function. Things that we've looked at along the way, domain, range, all those ideas. So what's the domain for an exponential function? 0. So if I say 0 to infinity, then 0 starts here, and it means I can't put any negative values in for, okay, so can I put negative values in here, Carlton? Okay, so that's an important distinction now to make, because we're used to the domain being down below, right? Along sort of like if I was typing, I wouldn't have to have a superscript, right? So now we're looking at x, which is the exponent. Okay, so that's an important point to point out. X can be any number along this axis, right? Any number. So what's the domain? Right, all real numbers, negative infinity to positive infinity. All right, what's the range going to be? 0 to infinity, but I need to know what to put around it in terms of my interval notation. Parentheses, because I can't be 0. I can't. There's no way I'm a 0, right? There's no number you can raise x to get 0. You can't double nothing. Well, you can. You get nothing. Okay? Anyway, don't start, right? You have to be quiet, Alex. All right? Because we can't get into trouble like Monday. Huh? I'm recording, yeah, but I haven't said anything wrong. All right, so notice this is going to get really, really, really small as x moves towards negative infinity. That fraction gets half as small, and it gets really, really teeny, but it's never going to equal 0. So that talks about the end behavior, or our horizontal asymptote. So let's skip down here. As x goes towards negative infinity, our function is getting smaller and smaller, so our function is approaching 0. Okay? And now let's look at the end behavior in the other direction. As x gets bigger and bigger, what's happening to our function? What's happening? It's approaching positive infinity, right, Mackenzie? So f of x approaches. Right? All right, so now let's take a look. We know our horizontal asymptote is the x-axis, or y equals 0. We have absolutely no x-intercept, because if we had an x-intercept, our value of our function is 0, and we just said we can't be 0, so none. And whenever we have a basic exponential function, our y-intercept is always 0, 1. So now I'm going back a little bit now to ask, is this function 1-to-1? I'm going back a little far into the beginning of functions. We talked about inverse functions. Is this 1-to-1? And how do you know, Josh? I see you going like this, or doing something with your hand. The horizontal line test, right? Right. If you draw a horizontal line anywhere through this graph, it touches it in one spot, which tells you it's 1-to-1, yes. So what does that mean all exponential functions have? If it's 1-to-1, an inverse function, right? Which is called a logarithmic function. But we have to wait 2 more classes to get there. Okay. All right. So that's exponential growth. Let's take a look at exponential decay. So now we're at 1/2 to the x power, which you could write like this if you wanted, because 2 to the -1 is 1/2. So that's just another way to write it. And if you look at your transformation, this says you are reflecting over the y-axis. So if you reflected this over the y-axis, you now get this function. Okay, so let's take a look. What's the domain for this? Yep, all real numbers, same thing. And let's just, for those of you who need a little work with negative exponents, let's just take a look at how, if we put a -3 in, we get the number 8. So g of -3 would look like this: 1/2 to the -3, which is, if you apply the negative sign to that, it just makes the reciprocal. So that's the same as 2 to the 3rd, which is 8. Okay, g of -2 is 1/2 to the -2, which is the same as 2 squared, which is 4. Okay, so notice that our lines now, the height of our lines are getting half the size as you go down. Here, the height of your vertical lines were doubling in length. Now they're being shrunk. Okay. All right. So the domain's the same. How about the range? Is the range the same? 0 to infinity, not including 0? Yep. Is it 1-to-1? Yep, they both pass the horizontal line test. That's how we know. Let me make that infinity a little nicer looking. There we go. Y-intercept, the same. 1/2 to the 0 powers 1 as well. Yep. No x-intercept. Horizontal asymptote, still your x-axis. And now the end behavior flips. Because remember, well, I won't go there. We'll just do it as looking at the, all right, as x goes to negative infinity, what's happening to my function? It's approaching infinity. It's growing without bound. And as x goes towards positive infinity, f of x gets closer and closer to 0. That's the end behavior. Okay. So your class activities now are a wide range of problems, from looking at transformations and looking at various parts of the graphing of exponential functions as well as applications. So you have almost a half an hour to work on those. Any questions before we go to the class activities, before we start them? All right.